Hello, Prof. Joe here. I wanted to make a video on the instantaneous center of zero velocity. And what this is it's a conceptual trick to help you solve relative motion problems. It's a way to quickly and easily solve some relative motion problems. So let's dive into it and see what this is. Okay, so I want you to imagine a bicycle. And that bicycle is going along the ground, as you can see up here. And ask yourself, what part of the bicycle wheel are all of the points of the wheel rotating about? The obvious answer, and the one that probably initially comes to your brain, is they're rotating about the hub, or the center of the wheel. But you have to realize that that's only in the relative coordinate system. That's only if you're on the bike. If you're the bike rider, then yeah, all the points in the wheel are rotating about the hub. But when you're off the bike, when you're earth fixed, that's not true. So let's go ahead and draw a picture of this wheel and highlight the points that we know about the wheel. Okay, so if we have a bicycle wheel and it's going along the ground, we know a few things about it. We know the hub of the wheel. We know the direction of its velocity. Right, that's going forward with the bike, because that's connected to the bike frame. What do we know about this point? We know that point is touching the ground. If we think of the rubber of the wheel touching the cement of the ground, those two are in lock with each other, just like gears, right? Unless the wheel is slipping, those are in lock with each other because of friction. How fast is the cement moving? Okay, that might seem like a silly question because obviously the cement's not moving in an earth-fixed coordinate frame. So that means the rubber that's touching that cement is also not moving. So the velocity at that point is 0. What do we know about the velocity at this point on the top here? Okay, well, the velocity at that point at this instant is actually going in the same direction as the bike, but it's going to be twice as much as the velocity of the hub. Okay. What we can find is we can actually relate the velocity of any point on the wheel to this point in the ground right here. That is what we call the instantaneous center of zero velocity. And it turns out that at any given instant, the velocity of every point on the wheel is actually rotating about the instantaneous center. Now, an instant later, the instantaneous center is going to be on a different part of the wheel because the wheel is spinning, and it'll be rotating about that point. So every given instant, there exists a point that has zero velocity, and at that instant, every other point is rotating about it. This is a very useful concept because we can very quickly determine the velocity of any point on the wheel. I can draw a line from the instantaneous center to any point, and the velocity is going to be perpendicular to that line. For these two, you can see, but you can do it for any point. Let's say I were to go over here. The velocity of that point is going to look like this. It's going to be perpendicular to a line connecting the instantaneous center to that point. Put another point over here. Velocity of that point, the combination of the spinning about the hub and the translation is going to give you velocity going down that way. So let me show you how we can use this to help us solve relative motion problems. There are generally 3 different ways that we can use instantaneous center to help us solve problems. And I'm going to illustrate all of those by thinking about a merry-go-round. So you have a merry-go-round, and that merry-go-round is spinning about a point on its center. Okay? Now this merry-go-round, as it spins, we're just going to focus on little pieces of it. So let's say there's a point A over here, and we happen to know the velocity of A. Okay? And we know the omega of the spinning merry-go-round. Now, let's pretend for a minute that we didn't know where the center of this merry-go-round was. We only knew those 2 things. We knew omega, and we knew the velocity of one point A. Let's say we only could zoom in on this part of it. Just this part of the merry-go-round is the only thing we could see. We don't know where the center is. How are we going to locate the center? Well, we know the velocity of any point on a body going through a rigid body motion is going to be perpendicular to a line that connects that point to the instantaneous center. So we can just draw a perpendicular line to our velocity. And then we need to figure out where along that line is it. Well, we know that velocity is equal to, if we go back to our rotational motion, we know that translational velocity is going to be equal to omega times the position from the center of rotation to the edge. So this would be our position of A with respect to IC, where IC is our instantaneous center of zero velocity. We can use our rotational motion equations, where we know that velocity of A, which in this situation is known, will be equal to omega times the position of A with respect to IC. If we want to know how big is this position so we can locate that center, we just do the math. It'd be our known VA over our known omega, and that's going to give us that position. And we could find the instantaneous center. Now the key here is that it doesn't have to be a merry-go-round. That any body moving through general planar motion is acting like a merry-go-round at every instant. The difference is the instantaneous center is always moving, and we can locate it using this method. Okay, let's look at another situation. Okay, in this situation we have a body. That body is moving, and we happen to know the velocity of 2 points. We'll call them A and B. This will be A, and this will be B. And let's just say that B is moving this way. That's our velocity of B, and A is moving that way. Okay, that's our velocity of A. Again, think of the merry-go-round. We know that these two are moving in these directions, and we need to find the center of that merry-go-round. How do we do it? Well, we know that the velocity is perpendicular to a position vector from that instantaneous center to the point. Okay, so let's just draw a line that extends perpendicular to both of these. You can see they cross at a given point. At this instant, this body is rotating about that instantaneous center as if it were a merry-go-round anchored right there at this instant. An instant later, it might be going somewhere else depending on the motion. But at this instant, that's the instantaneous center. And we know that because the position vectors, the position of A with respect to IC and the position of B with respect to IC, have to be perpendicular to our velocity vector. So that's the only place where they cross. And we've identified our instantaneous center of zero velocity. Okay, we'll look at one more situation. And let's say we have another body, and this body is rotating, is going through general planar motion, and we happen to have two parallel velocities. Let's say this is point A, and it's going this way, and then point B happens to be going the same way. Okay, we could try what we did on the last problem, where we draw a perpendicular line to both of them. This would be my perpendicular to A, and then my perpendicular to B would be the exact same line. And they don't meet at a point. They meet at a line. How would we figure that out? Well, we'd actually use the magnitudes of these two vectors. Looks like I drew my VB a little bit too long. They couldn't be the same magnitude, or there'd be no rotation. We'd just be in translation, right? So what we'd do is we'd say, well, I know that I'm going to have similar triangles. Okay. I could use similar triangles where the magnitude of my VA and the magnitude of my VB is going to be the same ratio as the total height of my VA triangle to the height of my VB triangle. And that's how we can locate this point, which is our current instantaneous center of zero velocity. We could say our instantaneous center, and then I'm going to label this position vector as the position of A with respect to IC, and then the position of B with respect to IC is a shorter one. Since we know that this one body has 1 omega, we can write our equation for VA that equals omega, position of A with respect to IC. And for VB, it's equal to omega, position of B with respect to IC. Okay? If we divide those two, the omegas cancel, and we get that the velocity of A over the velocity of B is going to be equal to the magnitude of these position vectors. So we can get that ratio and figure out exactly where that instantaneous center is. Now let me show you an example problem to see why it's helpful to know the instantaneous center. And to do that, I want to revisit a problem that I went through in my relative motion example on the previous video. And we're going to revisit it using instantaneous center. So why don't I write my givens really quick. We know omega OA is equal to 12 radians per second. Okay. And if you remember, we had calculated what our VA was. We have our O down here. We have our A up here. We know it's going at 12. And we know this is 0.3. So we said our VA, magnitude of our VA, we're supposed to find VB and omega AB. And we know that VA is going to be equal to omega OA times the position of A with respect to O, which is going to be 12 times 0.3. And this is in radians per second. That's in meters. So that'll be meters per second. 3.6 meters per second. If you notice, we're actually using instantaneous center right here. It's just this center is not instantaneous. This is fixed. This is an Earth fixed center. So we're using rotation. Instantaneous center basically allows us to use our pure rotation equations for any problem because we're finding that instantaneous center of zero velocity. If it's the center of zero velocity, we have pure rotation just for that instant. OK, so we know our magnitude of VA. Now what I want to do is approach our AB a little differently. I'm going to draw it. I think I have a bigger one here. Yeah, there we go. OK, so I'm going to draw my AB. OK, and now remember, one of the cases of instantaneous center we talked about is if you have a body and you know the velocity of 2 points, you can find its instantaneous center. That's what we have here. Now you might be saying, we don't know the velocity of B, and you're right, but we do know its direction. Okay? Its direction has to be up. How do I know that? Look at the picture. If OA is going this way, that means AB has to be going that way. And B is constrained, so it must be going up. So we know its direction. That's our velocity of B. We also know velocity of A because it's constrained with its own rod, the rod OA. So we know it's going this way. That's our velocity of A. How do we find the instantaneous center of zero velocity? We draw a line perpendicular to both of our velocities and see where they cross. Boom. We got ourselves the IC right here. Okay. Once we have the IC, we can actually use scalar equations, just like we did up here, to lay out both our velocity of A and velocity of B. This first equation, I determined the velocity of A using rod OA. Let's write the same thing using rod AB. And of course, I have to put a little bit more in my drawing here. This is 0.6 meters, and this is 30 degrees, as given on the drawing. So I can label my sides. I've got 0.6 sine 30, and I've got 0.6 cosine 30. Now I'm going to do the same thing I did up here, but looking at AB. The velocity of A is going to be equal to omega AB times the position of A with respect to IC, that instantaneous center. It's going to be equal to omega AB. What's our position of A with respect to IC? Well, that would be this vector right here going up. And you can see it's 0.6 sine of 30. I'm not putting in directions because I'm using all scalar equations right here. And I know my VA is 3.6, so I can put in 3.6 equals omega AB times 0.6 sine of 30. And I solve for omega AB, which is equal to 3.6 over 0.6 sine of 30 equals 12 radians per second. Okay, that was a little bit quicker than the way we solved it initially, and I got to use all scalar equations. Now the trick here is if you're using scalar equations, you can't forget your drawing, because directions do not come automatically. I only know the magnitude of omega AB. I have to figure out what the direction is by looking at my drawing. And of course, we already talked about that. The direction is going in the positive k, so I determine that. Okay, next we can write the velocity of B using our instantaneous center. The velocity of B is going to be equal to our omega AB times the position of B with respect to IC, which would be our 0.6 cosine 30. Plug that in. VB equals 12 times 0.6 cosine 30, which is that same answer we got before, 6.24 meters per second. And then again, we can't get the direction because we're using scalar equations, so we have to remember that we already know the direction because we drew it on here. Instantaneous center is really, it's a shortcut for solving problems quickly using relative motion. Why is it easier? Because the instantaneous center has zero velocity. If you can find that point and choose that as the point that you're going to use to solve the problem, it makes your equations more simple. Let's take a look at what we're really doing here. We know the equation velocity of B. This is our relative motion equation. It equals the velocity of A plus omega AB crossed with the position of B with respect to A. What we're really doing here is saying if we choose a point A that is the instantaneous center, then this term goes away. If this one is the IC, then there's no velocity, so that term goes away. We have a simpler equation, and we can use the scalar version as long as we draw a good picture and we know the direction. Hopefully that was helpful. What's the instantaneous center? Let me know if you have any questions.